Our presentation starts with Ashley. All right, it's all yours.
Hi. I swear, I'm going to do it. Okay. Hi, I'm Ashley, and I'm going to talk about what we can use GeoAI for in qualitative data. My position paper is a little, I don't want to say critical, but it definitely talks about the limitations of GeoAI with qualitative data, right? First, as a qualitative researcher myself, some of us are a little scared of technology in general, and we also really take into account the interpretive part of our data and of our job in terms of research. So I really wanted to think about the positives in this of the things we can do a little bit well and that can be helpful for GeoAI with qualitative data. And I'm hoping I learn a lot more about what I can do while I'm here. So for this, we're just talking about historical photographs. I wanted to talk about those for the lightning talk because of multiple reasons. The first is we can all interpret it together very quickly by looking at the photograph and seeing what's in it, right? Also, I had a lot of them. So it made it, for me, an easy choice to say, okay, I have like 370 photos in this folder. What can GeoAI help me learn about them? Full disclosure, I also used this to prep for my AAG talk. So if you see one or two of these slides again, no, you didn't, okay? In March, we're just, whoop, you can't see them, okay. So all of the photos that I examined were from the prior Creek tornado of 1942. So they're not the same quality as photographs we would take now, right? And also, a lot of them were photos that I took of photos in archives or museums or whatever. And what I did was I used a zero-shot image classification model called CLIP. And it's like 5 lines of Python. Well, it's more than 5 lines. It's 5 like kernels of Python code. And you give it different keywords and ask it to go through files on your computer. So I chose these and I was looking for storm damage. So I added a second kernel that was like, if it has more than 70% accuracy that you think it's storm damage, put it in this folder. That was really great for me personally because I was just looking for photos that I could use for another project. I wasn't trying to code every single photo I had. I wasn't trying to definitively say, you know, all of these photos are of storm damage and they're the only photos that I have of storm damage, right? I was like, I need like 3 good photos of storm damage that I can use to run these other analyses on for later. So this is an example of kind of what that looked like. So if you're a human interpreting this picture, right, it's downtown Pryor. There are buildings in it, right? But the model didn't see that. It saw the damage. It also didn't recognize really that there were people or that there was a crowd. Much to, I think it was Zal's point earlier, I have friends that have said if you put like different things like pants in there for people, you might get better results because it can like see that there are pants and if somebody's like turned away, whereas if you ask for a person, it might be looking for a face. So, but it created a folder of like good storm damage photos that I could use. And it also showed me a good part of what GeoAI does well for qualitative data, right? So with this, right, the torn away building, the storefront, is the focal image of the photo. And that's what the GeoAI was able to recognize, right? So it can detect those objects, it can sort these archival images for me, and it can say, like, this is what you have. But it doesn't give the context or the nuance that human interpretation would give. And so what we have to think about is neither approach is really neutral. It's both based on choices that we make how to use different keywords that might be better. And I have to say, like, this is what I'm looking for, even when I'm doing a human interpretation, right? So in terms of qualitative use for GeoAI, it's totally usable, but we have to think about the boundaries of what we want to do. So that's all I have.
Perfect.
Okay, so Education Management Information Systems, or EMIS, are essentially databases used by education ministries across the world for the purposes of education planning. They collect and store information at the school level on things like staffing, student enrollment, access to amenities such as water, internet, and electricity. However, in a lot of low and middle income countries, EMICs are way too costly and difficult to adequately maintain, and therefore there are large gaps in these databases if they even exist within a country system at all. This hinders the development of educational policies that are equitable across all student groups. So my project, I work with a team across 3 countries in Southeast, well, 2 countries in Southeast Asia and Nigeria, the Philippines and Cambodia. We're working together to create a collaborative and participatory regional EMIS database using data contributed by each of our partner members in order to gap fill educational indicators within each country's system. So the participating countries are the Philippines, Cambodia, and Nigeria. In the Philippines, we have explicit data arrangements with the Department of Education, whereby they contribute all of the data that we need. They have a really extensive EMIS system that gives us a really solid framework to develop GeoAI models. This framework is also kind of a cyclical process, so as they provide us data, we also give them generated estimates in return so that they can use for policy planning. The next country that's kind of our priority at the moment is Cambodia. They've specifically requested information at each of their schools on teacher shortages. So this is a really clear GeoAI problem that we have. Nigeria serves as a stress test for us. So they're obviously out of the Southeast Asia region. So Nigeria gives us a chance to test our models on a region entirely outside of our training domain. So there's a lot of issues that we're having with the modeling approaches right now. A lot of people have asked about foundation models and their potential to do this kind of work. The truth is that foundation models are designed to find a generalizable set of truths and patterns across all systems that predict and estimate socioeconomic indicators like teacher shortages. But fundamentally, these aren't the same across these different regions. They're not the same between Philippines, Cambodia, and Nigeria. Another way we've approached this is through standard geospatial domain adaptation strategies, which largely focus on sensor and resolution differences, temporal differences, and pixel distribution shifts. However, these methods are simply not enough because they're designed for how imagery and data changes, not how social meaning changes across different geographic boundaries. So in response to this, we've been thinking about more of a sociospatial domain adaptation framework. I think we have the first piece already where we've designed these domain adaptation strategies and foundation models that have a large and rich set of data sets that we can pull upon. However, what we're not considering are the last 2, the definition and measurement shift, whereby the definition of teacher shortages is different between Philippines and Cambodia. So how do we create a joint definition across different policy and cultural contexts that allows us to transfer models between different geographic spaces? The second thing that GeoAI has not accounted for and does not do well is accounting for this sort of spatial heterogeneity and the features within imagery and GeoAI datasets that actually estimate teacher shortages in different countries. So the fundamental problem is we have this really great dataset being contributed by these participatory partners, but fundamentally, how do you move a model trained in the Philippines to a country like Cambodia or Nigeria and predict accurately without simply projecting Philippines' cultural and policy context onto another country? Thank you.
Hello, everybody. My project is essentially looking at the ability of large language models with vision capability to derive meaningful information of urban neighborhood characteristics, socioeconomic data, poverty, tree canopy. And so I've developed 2 pipelines. One is a traditional kind of approach with segmentation and feature engineering and street view features. for predicting kind of pixel-based measures of poverty and tree canopy from street view images that are then aggregated up to a neighborhood level, like census block group, CG. And then the second pipeline, which is what motivated the project, is to look specifically at structured prompt engineering and the ability for GPT-4o vision to kind of mimic that traditional approach to also get predictions of poverty and tree canopy using different kinds of prompting and strategies, and to then compare the predictions across the two different approaches to benchmark data from official measurements from like census for poverty or GIE for tree canopy, and see which one does better, the traditional approach or this kind of out-of-the-box zero-shot LLM. So the context is kind of Phoenix, the Maricopa County area. And the idea is complicated by not just wanting to do prediction, but also trying to understand the implications of these foundation models for policy intelligence or policy inference. And so after first trying to validate whether or not LLM can even predict accurately neighborhood poverty, and to a better extent than the traditional approaches, which are validated and do a reasonably good job. The next step is then to see if we estimate a statistical model or a policy evaluation kind of context, would we get the same policy inference in the counterfactual that we had no census data on poverty? Would we actually get like, oh, this place-based policy improved poverty using the official data, and we get the same outcome or same inference if we're using just LLM, just through this kind of structured prompt approach. So that's basically the two kind of prong approach that I want to look at. So the first step is looking at just explanatory power. So basically regressing like official measures like poverty onto these geospatial prediction across the two different pipelines, the ResNet kind of segmentation model versus the LLM prediction, and see which one has more explanatory power. And then not just compare it to each other, but then you get a bunch of the socioeconomic census data for each neighborhood and put those in the model and kind of data fusion and things, and just see like, what do we add if we just have LM by itself, if we fuse everything together. And what we find is that the LLM in the red here, GPT-4, has about the same amount of explanatory power as a bunch of standard socioeconomic characteristics, like the share of ethnicity, human capital investments, things like this. Just the geospatial-based prediction by itself, and it far outperforms the explanatory power of kind of the traditional segmentation-based approach, which was very counterintuitive to what I thought. I thought I would be explaining why the traditional approach is better. So I'm not exactly sure why LLM vision is doing better, but that's something we want to kind of look at in the future. Then we also look at the geographic heterogeneity, kind of spatial dependencies or spatial heterogeneity across different types of census blocks, doing some kind of like quantile regression to see if the LLM is better of a predictor for very high poverty neighborhoods versus very low poverty neighborhoods. And what we find interestingly is that for the lower, like the most poor neighborhoods, it has lower explanatory power than for the richer neighborhoods, which is counterintuitive as well, because I would have thought it would be more or less accurate in the edge case, so like in the middle of the distribution, where it's really hard to differentiate like poverty versus non-poverty. But for the very high poverty, very low poverty, you look at a picture, you think it's pretty clear it's poverty or not. So I'm not sure exactly how to reconcile those results. But then moving into like the kind of a policy evaluation framework, basically the approach is it's not exactly, but for all intents and purposes, it's kind of like a spatial regression discontinuity design. So we have CBGs that are redlined historically from the 30s from Holt classification, basically a discriminatory housing policy that disinvested in the area and has a lot of literature showing the legacy effects that this is associated with larger poverty today to present day. And so basically just want to see like, will we recover the same treatment effect if we're just using a geospatial prediction? And just looking at poverty, what we find through bootstrap sampling and standard errors, that there's no statistically distinguishable effect between the LLM prediction and the census-based official poverty measurement. they had relatively the same positive effect. So if you were redlined, your poverty is higher relative to non-redlined, whereas the traditional model underpredicts what poverty is. So we have a little bit of a case for some optimism for the potential, just preemptive potential for LLMs out of the box, just to serve as potential missing data, filling missing data issues, potentially urban policy evaluations and things to this extent. Thank you very much.
Hi everyone. I want to talk about tabular data today. I think we have many discussions about image data and text data, not too much about tabular data. So actually tabular data is a very common data modality that we kind of use every day. Spatial tabular data is essentially just data that is georeferenced. So compared to image and text, I think tabular data is a little bit hard to model. Because all different reasons I put over there. So the data types are very different. They're collected from different sources. So it's quite different from pixels and words, right, in images and text. And also the presence of spatial effects. So, and I think the analytical goal is a little bit different. So in addition to making great predictions, we also care about how the data are generated, right? Their underlying processes. So that's why statistical models are still preferred, just like what Dr. Howell just talked about using spatial econometrics. However, just from my own observation, I see that there has been an increasing trend of papers that use machine learning together with explainable AI to do spatial tabular data modeling, especially with methods such as SHAD, LIME, or GeoShapley, the method that I've been working on. So explainable AI methods can help with the black box nature of machine learning. It doesn't address the issue itself, but it helps a little bit. For example, XAI methods can provide individual feature importance to explain how the model behaves, which kind of mirrors or overlaps with the local focus of spatial analysis and modeling. So in an earlier paper that I published, I find that this explainable AI approach, together with machine learning, can produce very similar results to spatial statistical models at parameter level. So what's the added value of machine learning? So just in my opinion, I think ML is still pretty flexible. Let's rely on the assumptions and can highlight like nonlinearity and the variable interaction that we don't often specify in our spatial statistical models. However, even though there are good adoptions of this approach, I think there are still big limitations. So first of all, explainable AI explains model behavior, but not the data behavior. So if the model is good, then we can sort of think the gap is small. We can infer back to about the data, how the data is generated. But when the model is bad, then the explanations generated from those explainable AI methods will be misleading and probably not very sensible. And just, you may agree or not disagree, but from my observation, I think there are not many great, there are great developments, but there are not like a very good GeoAI-based approach for spatial tabular data. I know there are developments on like graph neural network-based approach. You can geographically weight anything. But I find that sometimes they tend to over-stress some of the spatial assumptions and not as generalizable as some of the standard machine learning tools. So that's why we see still lots of papers using random forest, XGBoost to handle tabular data. And also there's a small data problem, right? We're not just dealing with big amount of data, we're also dealing with small data, which makes training a model challenging. So what's new in the tabular data area? So there's a recent method called TAP-PFN, published in Nature. We all talk about foundation model, but this is a different foundation model. It's not based on text or image. It's purely based on tabular data. So the essence is very similar to LLM. So it's trained on many causally generated synthetic tabular data, and then we can use the training data act as a prompt to predict any unseen data, and it has been proven to be very effective for small data sets. So in recent work, which is currently on review, we find that it's actually working pretty well across various spatial data generating processes. However, like the other foundation models that we talk about, they also have this spatial heterogeneity issue, or we need some localized fine-tuning to make it work better for our own data sets. However, I think this is kind of new to the tabular data world, so I hope this can be, I don't know if it's exciting, but it's definitely an interesting avenue to explore further. Yeah, thank you.
So I want to talk about synthetic data. There's growing interest in using synthetic data in training AI models in the geospatial community and beyond. And there's even forecast that by 2030, the data that we use to train AI models will mostly be synthetic data instead of coming from real observation. But in this work, we examined a risk of using synthetic data in model training, which is called model collapse. So model collapse occurs when we recursively train AI models using synthetic data generated by AI. And so as shown in this example, you can see that after several cycles of training on AI-generated data, generative AI models first tend to discard low probability events and features, and then start to generate nonsensical outputs after multiple iterations. So in this research, we examine what does model collapse means in the geospatial context? What does it mean for GeoAI? So we did a simple experiment on this. So we trained a conditional generative adversarial network to generate street view images, and we trained 5 successive generations of models. In generation 1, the model was trained on real street view datasets. And then from generations 2 to 5, the model was initiated from the previous generation, and then it was trained on images generated by the previous generation model. So we designed the experiments in this way to simulate and also to examine the cumulative effects of synthetic data in model training over time. So here's is some of our results. We made a visual comparison of the street view images over multiple generations of training. And you can see that in the second column, that is the real image from our dataset. And then we also show a few samples of the generated images for different generations. So one finding that we have is that even in the initial generations of model, these relatively rare spatial objects or visually small spatial objects like poles, traffic signs, and trees, and maybe people, these tend to get really blurry even in the first generations of model. And after multiple generations of training, for example, in generation 5, even for the relatively large spatial objects like the trees and also the buildings, so even for these objects, their appearance get blurry and non-recognizable as well. Okay, so besides the visual comparison, we also did a quantitative analysis of the model performance over generation. And so the assumption in these evaluations is that if a generative AI performs well, then ideally, if we apply an off-the-shelf object detector on an AI-generated image and on a real image, their accuracy should be similar. So based on this hypothesis, we apply this object detection model on the real image and also on the AI-generated image. And as you can see from the results here, again, these visually smaller objects such as bicycles, traffic signs, fence, bus, so their accuracy tend to degrade significantly even after just the first few generations. And after multiple generations, for example, in generation 5, we can see that even for the roads and also for vegetations in cars, their accuracy degrades significantly. Okay, so here are some takeaways from our results or from our research. So we talked about the core mechanism of what we call GeoAI collapse, which occurs after training AI models after over time and also after multiple generations. And so our research also highlights a practical risk of, so if unscreened AI-generated synthetic data start to enter these open repositories such as Mapillary and OpenStreetMaps and are being recursively used to train AI models, so there is a risk of GeoAI collapse. And our results also highlights the risk of what we call digital placelessness, which is when we use AI to produce images like we did before, there tends to be a homogenization of places in the generated data, so that can also be a contamination of our data space. Okay, so thank you.
Hello, this is Goodchild from UT Austin. So I would like to discuss about my presentation paper on functional spatial representation. So a lot of problems from scientific domains and societies require geospatial data, and in many times the geospatial tasks require data from different sources and in different data modalities. So here I put two examples. So for example, in ecology, the species distribution modeling is one difficult task. So for example, the current dataset, the GeoLife cliff, they require multimodal data such as Sentinel-2 images, Landsat images, climate tag, time series, environmental variables, and species occurrence, which is actually point observations. So another very different task from the atmospheric science domain is air pollution forecasting. So although they can also involve different datasets, but the two main dataset is meteorological data, which is in raster format, and the air pollution observation data, which is in point format. So now when we think about how do we handle the different data from different modalities, also we have the current vision and text foundation model can handle the text and videos, but geographic data has very unique characteristics, which motivate us to design some special architecture, such as what we call spatial representation learning, such as location encoding, polygon encoding, and polyline encoding. But now it comes with multimodal learnings. If we want to handle a geospatial task involving different data modalities, how could we integrate different data modalities to allow them to keep doing spatial reasoning from one modality to another? So here I just use one case study I recently read from a paper published in UCSB, I think 2 months ago. So what they are doing is air pollution forecasting. And as we discussed before, they are using two datasets, meteorology data and air pollution sensor data. So in order to allow the model to operate in both tasks, they do a very traditional approach, doing spatial interpolations. So they perform spatial interpolations to convert the air pollution sensor data into a raster format in order to learn new representations. But as the author noted, there are significant drawbacks for this approach because in order to make the resolution align with meteorology data, in the sensor dense in the area with dense observations, multiple sensors will fill into the same cells, which create an inversible data precision loss. So they cannot bring it back. So I think this is I think typical examples to show how the traditional data conversions will cause this what we call data position reductions, and also increase the data storage, and also lead to the MAUP problems. So how do we handle that problems? So here, in this position paper, I argue that spatial data, geospatial data require a multimodal AI with what we call functional spatial representations. So what do I mean by that? It basically means a representation learning method which aim at learning the new representations of geographic data as a continuous functions of space and time. So what do I mean by that? So the FSR basically means like given each location or time, it wants to map to a signals as a continuous functions instead of treating them as a discrete signals. So it has two advantages. First, the design as a continuous functions is more suitable for the conceptual definition for geographic data, for example, the polygon. Although many current, say, polygon encoders treat a polygon as a list of discrete polygon vertex, but polygon is actually conceptually a continuous surface. For raster data, although it is stored as a discrete raster pixels, but it represents a continuous field. So what if we want to learn the representations still also as a continuous functions, which will benefit the downstream tasks? The second advantage is it allows us to naturally express the geospatial relations between different data modalities. So as you can see here, so the trajectory vertex, the polygon vertex may not at the pixel center of the remote sensing images. But if we learn the new continuous functions, then we are not restricted to this fixed grid space, and we are easy to allow us to align different representations. So our vision is we can use functional spatial representations to learn different encoders and align them geographically. This is different from the geo-alignment Song mentioned this morning. But basically, based on our experiment, we found out this kind of multimodal pre-training can mutually beneficial different data modality encoders and help on multiple downstream tasks. Thank you.
Hi everyone, my name is Shashi Shekhar. I am from Department of Earth, Environmental and Planetary Science, and I'm also affiliated with Institute for Environmental Society. And I have been dealing with spatial decision making as long as I can remember since my PhD. So this is not a new topic. It has been the coupling of GIS with multi-criteria evaluation has been over 30 years of research actually, but the how machine learning can help us is the what I will try to just introduce. And if this is like the benefit of existing technology will be summarized, but if you would like to read more about the limitations, I encourage you to check the position paper on the Google Drive. So today I'm going to talk about the spatial composite indicators. What are they? Why should we care about them? And how can we improve them? So the use of spatial composite indicators are not new, and I'm glad that we have seen a couple of examples like sustainability index that Tony showed, or just air quality index. Their use of a single numeric index and SS of whatever the phenomena that you're interested in across different scales, regions, cultural contexts, and maybe useful to advanced knowledge. So let's look at this definition. They are single numeric indexes. So they are simple. They are just one score, and we combine various factors into the scores and help us to understand things that are not measurable on the field. So they are synthetic or performance-based. So there isn't something called that you can go and measure like social vulnerability. It's just a combination of education, income, race and ethnicity, and various factors like that. But they are useful so that it gives us an understanding of what they mean actually. Even though they represent spatially, and we can see a lot of maps of these indicators, they are pseudo-spatial, so they don't take into consideration of spatial heterogeneity or just how the phenomena is represented on space. And they are subjective.
So what goes into these scores or indices are defined by the decision makers or the practitioners most of the time. That means, continuing the example of social vulnerability, there's only 15 themes exist in social vulnerability index, even though demographics represented at least like 150 different attributes. So what can be done differently for spatial composite indicators? They can be spatial inherent, they can be scale dependent, and be policy relevant, because nowadays they are so popular because they're helping us to understand especially climate impacts. So how can we make these more relevant and representative? So this is actually tied to why we might need to help from machine learning algorithms. As a collaborative project with my colleagues, but not limited to them, because this was a huge project among 15 PIs and 10 different institutes, focusing on navigating the new Arctic and how the climate change and the environmental impact will affect the converging pressures on Arctic development. And for this particular project, we're also interested in like how integrating these diverse data sources, such as socioeconomic, environmental, infrastructural data sets, can provide a more holistic perspective on spatial vulnerability. So I'm not going to go into the model detail because it's freely available, and if you haven't checked iGuide platform yet, I would encourage you to do so. But we use a self-organizing map structure to reduce the dimensionality of these components, to better understand how these indicators are affecting each region. Thanks for your attendance, and I think I'm on time. Perfect.
Okay, good afternoon, everyone. My name is Cici. I'm coming from Spatial Science Institute at the University of Southern California. So today, I'm gonna step a little bit away from the technical part of GeoAI, which has been very heavily covered by our previous colleagues. So I'm gonna more lean towards the educational end to introduce one of our recent educational projects in an African context. Okay, why African? Africa is probably the most needed region that we need to take advantage of AI to empower the educational system because of current challenges out there, such as teacher shortages, a very severe classroom overcrowding, textbook limitation, and limited even lack of internet access and electricity, right? So our research goal to see how we can leverage AI to facilitate geospatial education, especially in one of the African countries, that is Tanzania, where I traveled to summer 2025. So I want to give the credits to our research team, 3 faculty members. In addition to myself, we also got Professor Xiaopang from Emory University, who is also sitting here, and Professor Wei coming from James Madison University as an AI expert. Together with our local collaborator, Ms. Yaya Lee, as the founding chair of SAY Foundation. So she is a true educator, has been working in Tanzania for more than 1 decade. Right, so I traveled to Tanzania summer 2025 and then stayed there for around 1 month. We select 4 local schools at different levels, all the way down to administrative university and the administrative school, and as well as 1 public sector, that's the Tanzania Health Institute. So with their introduction, we built up a collaboration with the Presidential Office of Tanzania. So what we do is we developed a very basic geographic classes, introducing what is a map, what is a projection, what is the vector data, what is raster data, etc., etc. Very basic concept. And we teach the class by human beings, so that's me, and also establish a generative AI assistant platforms consist of story map, ChatGPT chat box, AI-generated videos and visualizations and the interaction and animation. So that's how it looks like by using a smartphone. Okay, so in terms of procedure, we recruit totally 133 teachers and then divide them into two groups. So first taught by me, the other one taught by AI, and switch around. And then we conduct 2 rounds of quiz before and after to evaluate how the students improve. Okay, so let's see human AI PK round 1. All right, so in terms of knowledge gain, the group taught by AI with improvement of 2.1 points and taught by me with improvement of 2.3. Yay! I beat AI in this round. I'm so happy, very proud of myself. But we do see local variations across, say, gender and the age group, and then the level of professional. Okay, round 2. In terms of learning experience, right? So we can see the traditional teaching, human-based teaching, keeps students more engaged and more confident to ask questions. But in terms of other ones, such as easy to understand visualizations and stronger independent exploration, AI performs slightly better than human being. So I would say the second round is kind of ending up with a draw. Round 3. Okay, in terms of teaching task, very unfortunately, AI performs all the way better in all the teaching tasks in terms of understanding key terms, visualization, navigation, what is a GPS, data types, and the motivation to study geography. All right. So yeah, sadly I lose, but that's fine. So eventually, we also ending up with interviewing 33 teachers. To eventually, we have a consensus here in terms of pros and cons. But eventually, we say the blended approach works best, fitting into the local context. Okay, I don't have time to present all the key findings, but welcome to check out our paper, which is going to publish. And also I want to give the credits to Women in GIS for providing grants for geospatial work to support this work. Thank you very much.
Thank you. So glad to be here, and I'm going to talk about an area that I've worked in quite a bit, and that's applications of GeoAI in public health, focusing on opportunities and challenges. I want to talk about this specifically in the context of One Health. So this is looking particularly at infectious diseases at the interface of human, animal, and environmental health. And there's a variety of these that you'll probably recognize. Many of our vector-borne diseases, zoonotic diseases, COVID, influenza. There are vector-borne and zoonotic diseases and other environmentally mediated diseases, particularly waterborne diseases. And that's a nice FAO graphic over there on the right that kind of captures this. So there are a lot of components when you look at humans and animals and the environment, and we can measure these in a myriad of ways. In the clinic, studying wildlife, measuring the environment from the ground in situ measurements to measurements from space. And these give us a variety of data streams. So with human data, we have health records, traditional surveillance data, syndromic surveillance. Similarly, different types of data that we capture from animals, and then a myriad of different types of environmental measurements that we take that I think many of us are familiar with. And all of these data, and I think this resonates with a lot of the themes that we've talked about, they have heterogeneous spatial and temporal characteristics and associated attributes. So different spatial reference frames, scales, length of record, frequency, latency of reporting. How quickly do we get those data? And then in terms of the attributes, it's everything from species abundances often on the animal side. We may have clinical and confirmed cases, infection status. There's often genetic information. So really a lot of different types of information. And so what I think part of the pitch of what we can do with GeoAI is when we bring these together, we do a better job of predicting spatial and temporal patterns than with any individual data stream. So a haystack, I'll put forward to you that if we're looking at, let's say, a mosquito-borne virus, it's sort of like looking for a needle in a haystack, not an easy thing to go out and find. We may do this in different ways. We can put up mosquito traps and actually capture mosquitoes, take them back to the lab, test them for the presence of the virus. So that's one common approach. Another might be tracking climate or weather patterns that are conducive to the habitat of that particular mosquito. These each give us very different looks at the haystack. Actually sampling mosquitoes gives us a very clear picture of the haystack. We know in some places whether or not the virus is there, but we can't measure it all. On the other hand, if we look at weather or other habitat variables as a proxy, we can generally see the whole haystack, but it's a much more abstract picture. So in general, the idea is that putting these together are going to give us a better representation of that haystack than any of those sources alone. So opportunities. There's a lot of work using machine learning, deep learning, and associated methods for elucidating these very complex relationships. And we can do things like risk mapping. This is a West Nile virus risk map from South Dakota. Or forecasting. These are outbreak alerts from a malaria early warning system in Ethiopia. And we can scale these well, and they can enhance decision support through the risk mapping and the forecasting. But there are also challenges, and I'm just going to hit a few of these. One that we've actually talked about a lot in our discussions is data. This all depends very heavily on the data, and in particular, completeness of data, quality, error and bias, accessibility of the data. This is particularly an issue with health data, where much of it is not readily accessible to researchers or the general public. So these are all factors, trust and explainability are all part of it. A thing that we talked about earlier is uncertainty. So I'll just quickly make one final point. Often these events that we're trying to predict, whether it's a disease outbreak or it's a spillover event, they're not, they're like earthquakes or wildfires. We can say something about risk, but it's extremely different to predict exactly when and where that event is going to occur. So how do we deal with that uncertainty? Is imperfect knowledge better than none? Say the half-filled glass of beer is a good thing if you like beer. It's better than an empty glass. On the other hand, does it create new uncertainty and problems, analogous to the half-built airplane, where we look at that and we'll probably decide to walk rather than fly. So some things to think about, and I'd be happy to talk about these with you.
Hi everyone, my name is Lei from Texas A&M, and it's great to be here. And also I found it very challenging and both exciting to be a last speaker. On one hand, it's hard to contribute insightful ideas after hearing an entire day of exciting discussions, which is different from what has been told earlier. And secondly, usually the last speaker receives the longest and loudest applause. If you have been to a graduation ceremony, you know what I'm talking about. Not talking about me, but talking about the whole event. So today I want to talk about the step toward responsible GeoAI. And if you remember, I've been sitting on the responsible GeoAI table for an entire hour, collecting information, and hopefully contributing to the talk right now. So first I want to highlight the need for responsible thinking. And beginning in my early research career, I've been using diverse types of geospatial data together with GeoAI algorithms to identify people in need of help, damages caused by disasters, and better understanding human behaviors, especially adaptation behaviors under extreme events. So this is the one chapter has been collected by the Handbook of GeoAI, co-edited by Yuan and Song and Ingeo. So basically, we have been using large language model with social media to identify people in need of help, using large language and vision model with Street View to estimate hyperlocal damages. And recently, together with time series machine learning model and mobility, we're able to see how people adapt to extreme heat. For example, in Texas and Arizona, people prefer staying at home, both in daytime and nighttime. But somehow in California, during extreme heat, people want to go outside, go to the beach, thinking this is actually a nice weather rather than extreme heat weather. But today I'm not going to share the details of research and cheering for the advancement made by AI. I want to talk about some of the challenges we encountered in those disaster-related research. And the first thing is about who should access to this sensitive location information from GeoAI models and tools. For example, during disasters, a lot of people try to share information online, ask for help. But in the meantime, we can tell the non-government organization and government organizations offer different opinions towards sharing information online. And the reason is because by sharing those information, this information can be misused. Our original intention was sharing information can help first responders identify people in need of help. But in the meantime, we look at some of the news. For example, FEMA exposed personal data on 2.3 million disaster survivors, which can be used for some of the phishing and contact. But in the meantime, FEMA also offered tips to avoid the fraud and scams post-disaster by the leak of the disaster location information. And secondly is a lot of our research is trying to improve the model accuracy, and most of the time we're trying to maximizing the F1 scores. So this is one of the early models we developed a few years ago, and at that time we make a recommendation of choosing a model with BERT and CNN. But later on I started to realize, what about the false negative cases? Because every false negative indicate that people in need of help are not being found in the system. So maybe instead of maximizing the F1 score, we should focus more on maximizing the record rate so that we're identifying everyone in need of help, even though there's some misidentified cases in here. So that will fundamentally change the optimization process of the AI models we're developing. There's also another statement I want to make in here is that no data doesn't mean no need, because during time-sensitive and emergency events, there were a lot of cases we rely on data we collected to make decisions. But for people without power or people who are digitally overlooked or even disappeared in our digital world, their voices are basically overlooked by the AI models has been trained. So my argument in here is that no data itself could be considered a modality of data and should be considered in model training and model applications. So finally is that I think for the responsible thinking of AI and GeoAI or GI science in general, we're responsible for promoting GI science as a discipline and trying to bridge GI science with other disciplines. So this is one interesting example we started a few years ago, was when I met a colleague who come from biological experiments background, trying to use animal experiments to investigate the sleep behaviors. So most of the time they use fruit flies, they use mouse, those animals, to do the experiments. And they do have some observations about such as the relationship between social isolation and sleep loss, sleep quality. But later on they told me about one challenge, struggling, is they want to test the data on human beings, but they don't know how to do it. And I say, well, we have geospatial big data, we have AI models. We can use those data to help identify human sleep behaviors and also investigate its relationship with environmental changes, social and natural environments. So one study we did a few years ago is trying to see how does the social isolation triggered by the pandemic affect the sleep behaviors. And there are 3 different lines in there. The red line indicates the year when the latest sleep time during the year of the pandemic. So we can clearly see that the sleep behaviors has been shifted because of the social isolation reflected by human data. So another thing is that I do want to define what is a responsible GeoAI, which is a very challenging task. I started to search online, and the earliest definition or mentioning of responsible GIS in academic world was a work by Dr. Wright back in 2009. And later on in the AI world, responsible AI has been discussed for about 5 years now, and every company, every research group has diverse definition here. So what we did was trying to identify all the keywords, elements have been mentioned by relevant topics, including responsible AI, 3Es, and the other responsible conduct, geoethics concepts in there. We try to see which concept, which elements has been mentioned more frequently, and also which is more relevant to the geographical context, in addition to just the AI context. So this is what we come with the definition in here. It's about thoughtfully consider spatial context, human needs, and societal consequences. But in the meantime, also ensure data, insights, and decisions are safe, trustworthy, equitable, and beneficial to the public. I know I'm running out of time, so I will just move on to my final slide in here. Defining responsible GeoAI or defining relevant concepts can be conducted quickly by reviewing, but the more challenging part is practicing responsible GeoAI. So a simple solution is that we can create something like a checklist to start from research question definition all the way to the interpretation of the results. But here I do want to ask everyone one question. So who should GeoAI be responsible to? Is it responsible to you, to me, to the whole society, or to the user who are using these GeoAI tools? And secondly, what responsibility should it carry? Should it help you make decision? Should it help you to provide suggestions for decision, or only provide information and you make decisions independently? So I want to soften the tone a little bit. Instead of critically thinking about responsible GeoAI, want to thoughtfully integrate geoscience and AI in its real-world applications to better support the development of AI in the future. Thank you.